Today, we're going to describe an infinite dimensional Lie algebra on phase space. To keep things simple, let's just consider a standard run-of-the-mill, non-relativistic conservative system with n degrees of freedom. You know, things you learned in classical physics. One way to describe this system is to use energy. That's a very familiar way to describe it. We have the kinetic energy, which is just the sum of all the individual momenta squared over 2m, plus the potential energy, which is typically represented by a scalar function v of the coordinates. We call such a system conservative because the energy, in some sense, is fixed by design. That is to say, it's constant in time. So let's assume that and take a time derivative of the energy and see what we get. Now, the kinetic energy is a function of momentum only, so we can take a derivative with respect to p, and then using the chain rule, find p dot. And then for the potential energy, of course, that is a function of position only. And so again, we can take a derivative with respect to q, that is the gradient, and then take a time derivative of that coordinate, q dot. If you played around with physics before, you probably know that the momentum is defined to be the velocity times the mass. And so at the end of things, all we have to do is factor out the momentum and look at what we get. We get n equations that all basically yield the same result. Either the momentum can be zero, which is boring, or we can have this relationship between the time derivative of the momentum and the gradient of the scalar potential. In other words, what we have just stated is Newton's second law: the force is equal to the mass times acceleration. There's a reasonable footnote to add right here about the other factor of momentum. In the notation that we're currently using, we can rewrite all of this in a slightly more symmetric fashion, using or deriving what is sometimes called the Hamilton equations, which relates the time derivative of either p or q with the respective derivatives, partial derivatives of the energy. The first of these is pretty boring. It just represents the definition of momentum. That's actually not true. It is pretty interesting. Footnote here. The second of these, of course, encapsulates Newton's second law. The Hamilton equations, or what some old-fashioned people like to call Hamilton's equations, are pretty much the bedrock for understanding classical dynamics. And that is going to be our starting point. The astute viewer may have noticed that we've been talking about a single particle, or at least n degrees of freedom that all share the same mass. So as an exercise, generalize the definition of the energy to include n independent particles of a different mass, say m sub I, where I runs from 1 to n. Then show that Hamilton's equations, the Hamilton equations, still remain valid in their form. As many of you know, phase space is the stage on which the dynamics play out. It is the span of all of the coordinates and all of the momenta thought of as one big happy vector space, at least in the linear case. Phase space doesn't always have to be flat. Caveat footnote here. The physical states of a classical system can then be thought of as the orbits or the trajectories of the particle as it moves through phase space. And these are curves of constant energy. The physical observables then are those things that you can think of, that you can write as functions over phase space. Functions from phase space to the reals, or whatever. Here's where things start to get interesting. So let A be some function of phase space, that is to say some function of those P's and Q's. Now let's consider the time derivative of A. Because we have a conservative system, we don't have any explicit time dependence, and so we can just write this in terms of partial derivatives with respect to Q, Q dot, P's, P dot. Very nice, but it gets better. We have the Hamilton equations, which tell us what the P dots are and the Q dots are in terms of partial derivatives with respect to the energy. So let's go ahead and write that out. Now, aside from looking nice and symmetric and explicitly referencing the energy in terms of the time derivative, what we have here is something that at least the differential geometers in the audience are going to immediately stand up and start screaming about. To fully understand how useful this form is, let's generalize or abstract this representation of a dot, the time derivative of a little. Let's write this bracket out in terms of two functions from phase space to the reals, say a and b. In other words, let's write, say, the bracket with a and b is equal to this thing. To return to the specific from the general, note that the time derivative of any function over phase space a is given by the bracket of a with the energy function e. This bracket is just a binary operation on phase space on the vector space and was first really emphasized by Simeon Denis Poisson. Hence, it is called a Poisson bracket. For the second exercise, verify by explicit computation the following Poisson brackets. We now prove some interesting facts about the Poisson bracket, namely that the Poisson bracket is antisymmetric, it is bilinear, it satisfies the Leibniz conditions, as well as the Jacobi identity. Proof. Antisymmetry pretty much follows by inspecting what the bracket looks like, and bilinearity is just a natural property of the fact that we've got partial derivatives involved, because they are in fact linear operators. Similarly, the Leibniz condition, this thing here, this is basically the product rule. It's a fancy word for the product rule, and because the Poisson bracket is made up of partial derivatives that satisfy the product rule, so too does the Poisson bracket. Finally, the Jacobi identity is something that you're just going to have to do, and you're just going to have to do it by yourself, and you're just going to have to work it out, and everybody has to do it once, and so you may as well do it now if you've never done it before. But if you're one of those differential geometers we mentioned earlier, you probably already know that this is just the condition that the two form associated to the Poisson bracket is closed. There's a really interesting corollary that comes immediately from knowing these facts about the Poisson bracket that you might recall from our introductory video, is that the Poisson bracket is a Lie bracket, and therefore the vector space of functions over phase space is a Lie algebra. And so we are done. Next time, we're going to explore the Lie group associated to this Lie algebra. Stay tuned.